In this video, we are going to talk about the magnetic properties of coordination compounds based on valence bond theory VBT. Magnetic moment can be measured by magnetic susceptibility experiments. Magnetic moment can be measured by magnetic susceptibility experiments. By using that result, we will get information about the number of unpaired electrons and hence the structures adopted by the metal complexes. So in order to understand how many unpaired electrons are there and in order to understand about the structure of the compounds, we are able to use this magnetic susceptibility experiments. As a result of that, we will get the magnetic property of the compounds and we are able to predict how many unpaired electrons are there, what is the structure of the compound, etc. We studied the property of magnetic data of coordination complex of first transition series and it revealed so many complications. We are getting different answers for different complexes and by using VBT we try to explain it and that we are going to deal in this section. Metal ions up to 3 electrons in the d orbitals like titanium 3 plus which is having d1 electron, vanadium 3 plus which is having d2 electron and chromium 3 plus which is having d3 electron is not having much trouble because vacant d orbital, 2d orbital is already vacant in this cases. D1 means 4d orbital is in vacant form and we are able to use D2 sp3 hybridization without any trouble because vacant orbital is present. In the case of D2 also vacant d orbital is already available. In the case of D3 also vacant d orbital is already available. So in all these cases the magnetic behavior of the free ions and their coordination entities is similar. When more than 3d electrons are present, they need to pair electrons to make vacant d orbital if the inner d orbital is taking part in bond formation. If more than 3 electron is there, pairing will be required in order to use inner d orbital for the bond formation. Example D4. If the configuration is D4, it is happening in chromium 3 plus Cr2 plus or Mn3 plus. You can see in the figure only one d orbital is vacant there. So in order to make D2 sp3 hybridization, pairing is required in this case. D5, Mn2 plus and Fe3 plus is having D5 electronic configuration. There also, if without pairing, D2 sp3 hybridization will not occur. D6 configuration. Fe2 plus and CO3 plus is having D6 configuration. There also, in order to make the last 2 d orbital for hybridization, we want to make pairing. Right. We can see few examples. Mn CN6 3 minus. Their manganese is in plus 3 oxidation state. Therefore, Mn3 plus the configuration is 3d4. We done it earlier, okay. Mn3 plus is having 3d4 configuration. We written here. Mn3 plus is having 3d4 configuration. So, it is having 3d4 configuration. In order to make D2 sp3 hybridization, this inner d orbital we want to make vacant. For that, pairing will occur here. That is, the electron from this second last d orbital will go and pair with the first d orbital. After pairing, we are able to see 2 unpaired electrons there and 2 vacant d orbital. So this compound will show magnetic moment of that 2 unpaired electron. When we are doing magnetic susceptibility experiment, it will show the magnetic moment of these 2 unpaired electron. Another example, FeCN6 3-. Iron is in +3 oxidation state. Fe3 plus is having D5 configuration. So what happens? In order to make the inner d orbital for bond formation, hybridization, pairing will occur here. The electron from the last orbital will move to the first one and second last will move to the second one, and pairing will occur there. So after pairing, we are able to see only one electron is unpaired there. So this compound will show a magnetic moment of this one unpaired electron. Another example, MnCl6 3-. Manganese is in +3 oxidation state. Mn3 plus is having D4 electronic configuration. In this case, since chlorine is a weak field ligand, it will not undergo pairing. Instead, it will show sp3d2 hybridization. sp3d2 hybridization, that is, outer d orbital is being used for bond formation. So in this case, this 4 electrons, unpaired electrons, will be remaining there as such. So this compound will show magnetic moment of 4 unpaired electrons. Now FeF6 3-. Here also iron is in +3 oxidation state, therefore D5 configuration. Since fluorine is a weak field ligand, here also pairing will not occur and these 5 electrons will be there unpaired. So this compound will show magnetic moment of 5 unpaired electrons. Similarly, when we are checking in this case COF6 3-, this compound is also paramagnetic with 4 unpaired electrons. C2O4 thrice 3-. This is a diamagnetic compound. Actually, when we are considering C2O4 2- as a weak field ligand, this is not the situation, but in this case, only in this case, C2O4 2- is acting as a strong field ligand. Therefore, pairing will occur here. As a result of that, it is a diamagnetic compound. So, in the case of compounds formed from first transition series, different type of magnetic moments value for magnetic moment we are getting, and from that, according to VBT, we are able to conclude that MnCN6 3-, FeCN6 3-, COC2O4 thrice 2- are inner orbital complex. D2 sp3 hybridization in all these complexes. Out of this, MnCN6 3- is paramagnetic, FeCN6 3- is also paramagnetic, but COC2O4 thrice 2- is diamagnetic. MnCl6 3-, FeF6 3-, COF6 3- are outer orbital complex, or sp3d2 hybridization is seen in this case. MnCl6 3 minus is having 4 unpaired electron. FeF6 3 minus is having 5 unpaired electron. COF6 3 minus is having 4 unpaired electrons. So they will be showing the magnetic moment based upon this number of unpaired electrons. Here, one important thing to be noted is when this question is asked MnCl6 3 minus, it is showing a magnetic moment of 4 unpaired electron. Why? Don't use the answer Cl minus is a weak field ligand, so it will not undergo pairing. You can use this answer, that is, it is a outer orbital complex, or it is having sp3d2 hybridization. This is the conclusion based on VBT. Here we told this just for make your learning easier. That is dealing in the next theory, not in VBT. According to VBT, when you are explaining this, don't use this point. Instead, you can use outer orbital complex and it is having sp3d2 hybridization. Clear? So, MnCl6 3 minus, FeF6 3 minus, COF6 3 minus is having sp3d2 hybridization and they are outer orbital complexes. Limitation of this valence bond theory. It cannot explain the color or spectra of complexes. Not able to say why some complexes are colored. The theory doesn't give any idea about the kinetic stability of complex. It does not distinguish between weak or strong ligands. That distinguishing not done here, but in order to make our studies easier, we just talk about it during this discussion. It does not predict exact structure. It does not give any quantitative interpretation of magnetic data. Why some are having 4 unpaired electron, why some are having only 1 unpaired electron, like that things not able to predict more. When we are talking about strong and weak field ligands, we are able to say little more clearly about it. But this theory didn't talk anything about strong or weak field ligand. So it is not able to give a quantitative interpretation of magnetic data. So these are the limitation of valence bond theory.